Hi everyone, this is Mrs. J, and today we're going to be working with complex numbers. But first, please pause the video and give this warm-up a try. Alright, go ahead and check your work here. Graphically, our vertex is at 0, -4, and we have a downward facing parabola. So you can see that this graph never crosses the x-axis and therefore has no x-intercepts, and therefore has no real solution. Algebraically, with the square root method, I isolated x squared and took the plus or minus square root of both sides. Again, there are no real solutions to this because you can't take the square root of a negative number for a real result. Now today, we will be addressing this issue of, well, what do we do if we have the square root of a negative number? So that's what brings in this concept of complex numbers. So first we're going to talk about what's called the imaginary unit, which we call I. So I, in math, whenever you see the variable I, the definition of I is that I is equal to the square root of -1. So this was kind of a workaround for when we end up with the square root of a negative number. So instead of just saying that there's no solution, we have a way to describe a different type of solution. So anytime you have the square root of a negative number, we can now go further and actually provide a complex solution. So again, just by definition, I equals the square root of -1. So here I want to talk about a couple powers of I. Of course, I to the power of 1 is just I. We would always just leave it as I. But this next one especially is very important when it comes to simplifying powers of I. So I squared, just by definition, we really need to know this. I squared is equal to -1. This one is extremely important for us when it comes to simplifying our answers. So if you ever see I squared as part of our answer, we won't leave it like that. We'll write it as -1. Now, if we have I cubed, well, if you think about it, I cubed is just I squared times I. And we know that I squared, over here, anytime we see I squared, it becomes -1. So this just becomes -1 times I, which is -I. So essentially, we're just looking for I squareds to turn into -1. And we can kind of follow that same logic for I to the 4th. We know that I to the 4th is simply I squared times I squared. I squared is -1, I squared is -1, -1 times -1 is +1. So anytime you have a power that's a multiple of 4, it will eventually simplify to to just +1. But again, the one you really need to know is that any I squared, we will simplify it to be -1. So now that we know about this imaginary unit I, we can now simplify radicals that have a negative in the radicand. So let's start with this first one. Anytime you see a negative inside a square root, the first thing I would like you to do is just put an I out front and get rid of the negative. That's the first thing you need to do. So now that we've taken care of the negative, all we need to do is simplify the square root. And we know that the square root of 25 is just 5. So this answer is just 5i. We treat I just like any other variable in terms of where we write it. We always write it after the coefficient. Here, I do want to point out, a lot of people say, okay, the square root of 25 would be plus or minus 5. Here, I don't see a plus or minus in front of my radical. So in this case, they are only looking for the positive square root of this value. The only time we do a plus or minus is when we are the ones initiating the square root. So if we're the ones putting the square root in the equation, then there needs to be a plus or minus, or if there were already a plus or minus there. But in this case, since there's no plus or minus, it's implied that they're only looking for the positive square root of -25. So we have 5i. Let's try this next one together. Square root of 72. So I'm going to start by taking care of the negative. And then from here, all I need to do is simplify this radical. Remember, we did this problem in a previous set of notes. We know 72 is simply 36 times 2, and 36 is a perfect square. So this becomes 6i root 2. So the square root of 36 is 6, and that joins the I out front, but the 2 will remain in the radicand. All right, let's try this last one. Here, the first thing I'm going to do is take care of the negative on the inside, and I'm just going to put a 5 on the outside. Notice that the negative on the outside is still there. This has no effect on this. So now all I need to do is simplify the square root of 9. The square root of 9 is 3, so then I'm going to multiply that by negative 5, and we get negative 15i. And there you have it. So now we have a way to work with square roots of negative numbers. All right, now it's your turn to pause video and try these 3 on your own. All right, go ahead and check your answers real quick. And again, I really recommend always just taking that first step and addressing the square root of negative 1 and then simplifying the square root after. All right, so now that we know what an imaginary unit is, now we're going to talk about this broader term called complex numbers. So complex number is any number that is written in this form of a plus bi. So a we call the real part of our equation, and this bi term, we call this the imaginary part. And a and b, those coefficients, both must be real numbers. So you can see that the real part does not have an I, and the imaginary part has an I. And in standard form, you always write the real part first and the imaginary part second. It's okay if the real part is negative. It's okay if the imaginary part is negative, as long as it's written in the correct order. Now, while this complex numbers actually describes a very large it's kind of a blanket term for a lot of different numbers. So if we break this down, we can break it down into what are called real numbers. So real numbers occur when your b value equals 0. This is when b equals 0. So if b equals 0, you don't have that imaginary part, so we could just call it real. We could still call it a complex number. If you don't see an I, technically it is still a complex number, but the more specific term for that would just be a real number. So it's essentially any number without I. Now here, imaginary numbers are any numbers that do have I. Now if they have a real and an imaginary part, we would still call this an imaginary number. 2 plus 3i is an imaginary number. 9 minus 5i is an imaginary number. But within that category, you can get even more specific to what's called a pure imaginary number. It's when your a value is equal to 0. This is when a is equal to 0. So if you only have the imaginary term, we could call this a pure imaginary number, but we could also call it an imaginary number, and we could also call it a complex number. So again, complex is the most broad term for them, and you can get more specific depending on what a and b are. All right, let's try this next problem together. So here we have two complex numbers that are equal to each other, but they have variables inside. So you can see we have 2x minus 7i, and we have 10 plus yi. We need to solve for x and y. So using logic, if two complex numbers are equal, then we know that their real parts must be equal, and we know that the imaginary parts must also be equal. So to solve for this, I simply take the real parts and I set them equal to each other. So I get x equals 5. And then I take the imaginary parts and I set them equal to each other. And you end up with y equals negative 7. So again, if you ever see this scenario where we have two complex numbers equal to each other with some variables to solve for, set the real parts equal and set the imaginary parts equal. Okay, go ahead and pause the video and give this one a try on your own. All right, go ahead and check your answers here. So here you can see that I set my real parts equal and I got x equals 7, and then I set the imaginary parts equal to each other and I got y equals negative 20. Now we're going to practice performing some operations with complex numbers. Specifically, we're going to do addition, subtraction, and multiplication. So when you're doing basic operations, I acts like any other variable. When you're adding or subtracting, you're simply combining like terms. So let's try this first one. We have a complex number plus another complex number. All we need to do is combine like terms. But first, I'm going to rewrite this without the parentheses. In this case, the parentheses don't really do anything, so I can just rewrite it. And then all I'm going to do is I'm going to add my real numbers together, and then I'm going to add the imaginary numbers together. So this gives us 13 plus 3i. And notice when I'm adding negative I and 4i, it's just like adding any other term with any other variable. I'm simply adding or subtracting the coefficients to combine like terms. Now for part B, same idea, but we do need to watch out that we distribute the negative to the second complex expression. So we have 7 minus 6i minus 3 plus 6i. And now all I need to do is combine like terms. I'm going to combine the imaginary and the real portions. So 7 minus 3 is 4. Negative 6i plus 6i is 0. So this just becomes a real number, 4. Now let's try doing some multiplication. So when we multiply terms with I, it's just like multiplying any other variables. Again, we do just need to remember one super important step when we're simplifying. We need to remember that I squared is always going to simplify to negative 1. So that's the one thing to watch out for. All right, let's do our multiplication. Here I'm going to distribute 4i to negative 6 and to I. So 4i times negative 6 is negative 24i. And then we have plus 4i squared. And again, here we have this I squared term, which we do need to simplify. So 4 times negative 1. And so that leaves us with negative 4 minus 24i. So our final answer should never have I squared in it. And our final answer should be in standard form. So real part and then the imaginary part. All right, now let's try a binomial times a binomial. We're going to FOIL it out. So we can start with 9 times negative 4, which is negative 36. 9 times 7i, so 63i. And then here we have negative 2i times negative 4, so positive 8i. And then we have negative 2i times positive 7i, so negative 14i squared. We will combine like terms. So you might notice here we have 2i terms that we can combine. So that gives us negative 36 plus 71i minus 14 times, remember this I squared term, we will always simplify to negative 1. And now I just need to take one more step. It becomes plus 14, so I just need to combine like terms, and then I'm done. So negative 22 plus 71i. All right, so now it's your turn to try these on your own. Pause the video and give them a shot. All right, go ahead and check your work here. For part A, please make sure you distributed the negative before you combine like terms. And for part B, we FOILed it out. Make sure you simplified this I squared to negative 1, and please make sure you combine like terms correctly. All right, so next we're going to talk about this idea of complex conjugates. So this word conjugates, we will return to this later on this year. But pairs of numbers in the form of a plus bi and a minus bi are called complex conjugates. So you can see what makes them conjugates is that the signs of your imaginary term are opposites. So one is positive and one is negative. That first term, your real term, should remain the same. So complex conjugates are kind of cool because something special happens when you multiply them together. Let's see. Let's FOIL out this expression. We have a times a, which is a squared. So we're doing FOIL. And now let's do a times negative bi. That would give us negative abi. And then we have bi times a, so plus abi. And then we have bi times negative bi, so that'll give you a negative b squared I squared. Now let's combine like terms. Well, you see that we have negative bi and positive bi. So that will become 0. That cancels out. And then we see that I squared term that we know becomes negative 1. So now we have a squared minus b squared times negative 1, which just becomes a squared plus b squared. So you can see when I multiply complex conjugates, the imaginary term disappears. So this is going to be a really useful strategy for us when we need to turn something imaginary into something real. All right, let's practice this together. Let's multiply negative 5 plus 2i by its complex conjugate. So negative 5 plus 2i, the complex conjugate would be negative 5. Remember, your real term stays exactly the same. That does not become opposite. It's your imaginary term, so it becomes minus 2i. Let's see what happens when we FOIL this out. Negative 5 times negative 5 is 25. And then we have negative 5 times negative 2i, so positive 10i. And then we have 2i times negative 5, so negative 10i. We have 2i times negative 2i, so negative 4i squared. So you can see again here, our I term cancels out. We know that this I squared term right here will become negative 1. So we have 25 minus 4 times negative 1. So 25 plus 4, so 29. So you can see that when I multiplied by its complex conjugate, the imaginary term disappeared and I'm left with just a real number. Okay, go ahead and pause the video and give this one a try. Go ahead and check your steps here. So again, when we multiply by the complex conjugate, which should be 7 plus 4i, our imaginary terms disappear. This I squared turns to negative 1, and we're left with just a real number. All right, the last thing we're going to do is we're actually going to kind of rewind and go back to that problem from the warm-up. So if you remember in the warm-up, we solved this graphically and algebraically and found that it was no real solution. But now we know about the imaginary unit I. So let's see if we can now provide a complex solution. Let's do the same step. Let's use that square root method. So I'm going to isolate my x squared term, and then I'm going to take the plus or minus square root of both sides. So here, now we know how to simplify this. So first I'm going to put an I out front to take care of the square root of negative 1, and then all I need to do is simplify my radical. Square root of 4 is 2, so we have plus or minus 2i. So we have two solutions to this, positive 2i and negative 2i. So from here on out, you'll see that I will be asking for all possible solutions. So we will no longer stop here and say no real solution. We will now give our complex solutions. All right, that is all for today's lesson. Thank you so much for watching.